Hello and welcome to the solutions of the tutorial number 4 on heterogeneous catalysis. So straight away we go to the question number 1. So these questions were given to you as an assignment. I hope you have attempted to solve it. So the first question deals on an Elie-Riedel mechanism, and the question has two parts. So the first part asks you to prove that when the pressure of this gas molecule B is too high, the rate limiting step is the collision between A and B. So now let's try to write the rate of these kind of Elie-Riedel mechanism. The rate is given as some rate constant Z multiplied by equilibrium constant Ka Pa divided by 1 plus Ka Pa, and this is multiplied by Pb. Sorry, there is a little mistake here. This would be in terms of B because the gas B is getting absorbed. So it would be like this multiplied by Pa. All right. And so the consideration is that when Pb is too high, so at a very high pressure of Pb, what happens that Kb/Pb is so high that we can neglect 1 with respect to Kb/Pb. So this entire thing would now be reduced to Z multiplied by Kb/Pb divided by Kb/Pb multiplied by Pa. So, or in other words, this would become Z multiplied by Pa. So that means the entire mechanism would be first order with respect to the gas molecule or the species A. So it is only dependent on Pa. So whenever it is dependent on the gas molecule of A, so we can tell that this entire reaction mechanism is determined by the collision between the gas A and B, because the only action the gas molecule A is having in this mechanism is to have a collision with B. So therefore the collision is the rate determining step. Okay, so I hope you have understood. So now we come to the second part of the question. The second part of the question says that when Pb is too low, so what would happen? So when Pb is too low, therefore the reverse would happen. We can neglect Kb/Pb with respect to 1. All right. So therefore the above equation would transform into is equal to Z Kb Pa multiplied by Pb, or in other words, this entire reaction would be of second order because the reaction would be governed by the concentration or the pressures of the two types of gas molecules A and B. So therefore the kinetics is governed by the second order. Okay, so now we move on to the second question. So in question number 2, it says that two gases, ammonia and deuterium, are getting adsorbed simultaneously but in two different sites. And also it says that the deuterium dissociatively adsorbed. So that means when deuterium is getting adsorbed, it breaks into two deuterium atom. Okay, so D2 goes into two D atoms. D2 molecule is breaking into two D atoms. And then the deuteration reaction happens. So one of the D actually replaces one of the H of the ammonia. So an H2D gas goes out and we are left with 1D. Anyway, so this portion is not relevant to us for the rate law. We only concentrate on this part. So now what's given that for D2, its partial pressure is P and the the equilibrium constant is K. Means equilibrium constant for adsorption means this is equal to the K is equal to the rate constant of adsorption divided by rate constant of desorption. And we assume that the partial pressure of NH3 is P prime and the corresponding equilibrium constant is K prime. And it's also given that for deuterium, Kp is negligible with respect to 1. And it asks us to find the rate law or suggest the rate law. So what we do here, so let's first write that rate is equal to obviously Z multiplied by theta NH3 multiplied by theta D2. So these are the two fractions of adsorption of the two gases on which the rate would depend. So what is theta NH2? Of course, we can write that the theta NH2 is K prime P prime divided by 1 plus K prime P prime, this one, and multiplied by theta D2. So for theta NH3 we have no confusion because straight away we can write the equation obtained from the Langmuir's theory. So this is the expression of theta according to Langmuir's model. So now the question is, what is theta D2? So then we can try to find it out. So theta D2, how we can find it out? So let's find out that rate of adsorption is equal to the rate of desorption, right, for D2. Or in other words, the rate of adsorption is actually rate constant of adsorption multiplied by the pressure of D2 or partial pressure, that is P, all right, and then multiplied by the fraction of empty spaces, of vacant spaces, so that we can tell it 1 minus theta D2 is equal to the rate constant for desorption multiplied by now the fraction that is required, or the fraction that is occupied by D2. But you see here that whenever we talk about the desorption, you need to know the fraction that is occupied, but for one D2 gas molecules to form, you need to take two occupied portions of D. That means you need two occupied fractions. Okay, so 2D makes D2. So therefore, this portion would be dependent or would be treated as a second order rate law. So therefore, it would depend on theta D2 square. All right, and similarly over here, whenever we talk about the empty portions, the fraction which is unoccupied for the fresh adsorption of the remaining D2 gas, again you have to think that there should be two available fractions, okay, or that means, sorry, the two available sites. So therefore its dependency would be also squaring up. So we have an equation like that, and from that we can express theta D2 is equal to, if we solve this thing, it would ultimately come as root over of Kp divided by 1 plus root over of Kp, and it is given that Kp is much less than 1, so it goes to root over of Kp, because if Kp is much less than 1, we can also neglect root over of Kp with respect to 1. So therefore this entire expression would now take up a form like that, multiplied by root over of Kp. So that's how the rate law appears. All right, so I hope you understand. So the main thing, the trick is over here. So whenever we have a dissociation process going on, we have a second order rate dependence both on adsorption and desorption, because you need twice the fraction of empty spaces, and also you need to have twice the fraction of vacant spaces. So sorry, but twice the fraction of occupied spaces for desorption, and you need twice the portion of or fraction of the uh, vacant spaces for adsorption. All right, so let's move on to the next question, question number 3. So question number 3 asked you to mention some industrially important heterogeneous catalysis. So therefore, I have listed some of the important examples in a form of a table. So in the left hand column we have the solids, and in the middle column we have its particular function, and then the last column is about the particular examples. So let's first start with the metals. So some solid metals, for example iron, nickel, platinum, silver, they help us for hydrogenation and dehydrogenation reaction industrially. Remember, all these examples are done not on a research laboratory basis, but actually these are done on a regular industrial scale application. So next is the semiconductor oxides and sulfides like nickel oxide, zinc oxide, magnesium oxide, or molybdenum sulfide. So they perform oxidation reactions or and desulfurization reaction. And then we have insulating oxides like alumina, silica, magnesium oxides. So they are used for dehydration. In fact, there are many commercially important products that needs to be kept away from moisture, so where these kinds of substances are readily used. And then we have solid acids, for example phosphoric acid, and also we have some like in some cases we have some sulfuric acids also, and aluminosilicates and zeolites. So what happens that for these acidic solids help us for polymerization reaction, isomerization reaction, cracking of petroleum, and alkylation, etc. So remember, so these acids sometimes can be used as a solid support. These are not like freely available homogeneous reactions like a free solution. So these groups like phosphates and sulfates, etc., they are used as a solid support, with the solid support. And zeolite is a special kind of porous acidic solid. It is a mineral, okay, and it helps us to perform shape and or size selective catalysis. All right, so these are the few basic examples that I think you should remember, okay, and objective type questions may be asked. All right, so next we move on to question number 4. So in question number 4, we have been given a graph plot, and you see 1 over V versus 1 over P, and some data points are there. And we have been asked to calculate the surface area of the solid surface in meter square, where the cross section of the adsorbed gas molecules, means the cross sectional area, is 0.43 nanometer square. So let's first try to understand what it is given. So it's given that the inverse of the volume adsorbed in centimeter cube at standard temperature and pressure, and this is 1 over P, and some graph plots and some data points are given. And so this problem deals with the adsorption of a gas on a certain solid catalyst. So from the adsorption isotherm data, this plot have been generated, and we have to assess the surface area of the solid from this adsorption data. So now let's proceed with the concept theta. So what is theta? Theta is the fraction of gas molecules that is adsorbed. So that means the fraction of gas molecule, the number of gas molecules N is currently adsorbed on the surface divided by Nm, or the total number of gas molecules required to form a complete monolayer on the adsorption surface. So that means here I would try to illustrate with a picture that suppose this is the total surface, okay, and so how many vacant available sites are there? So Nm stands for the total available vacant sites. So if we require certain n number of molecules to cover it completely, so this entire number, this is called Nm. So number of molecules required to to form a complete monolayer actually signifies the total number of possible vacant adsorption sites, and N represents the number of gas molecules are actually adsorbed on the site. So the maximum value of theta is 1 unity. And the same thing then we can express that this N over Nm could be the volume of gas molecules adsorbed at any instant divided by the volume of gas molecules required to form a monolayer. So the same thing, theta. So now we know from the Langmuir's model that this theta, or V over Vm, corresponds to some constant multiplied by the partial pressure of the gas divided by 1 plus constant multiplied by the pressure of the gas. So therefore what we do, that we can take the inverse of this equation. So that means Vm divided by V could be 1 over Ap plus 1. Alright, and then what we can do is, or we can take 1 over V is equal to 1 over A Vm multiplied by 1 over P plus 1 over Vm. So now you see we get a linear equation which is almost like y is equal to mx plus c. So therefore if we plot 1 over V versus 1 over P, we get a straight line with an intercept of 1 over Vm and the y-axis. So that is exactly what's happening here. So 1 over V has been plotted with 1 over P. So now it would give a straight line. So all those 4 plots are there. The best fit should give us a straight line, something like that. So the slope of the straight line is actually 1 over A multiplied by Vm, and the intercept when 1 over P is equal to 0, so that is here, okay. So the intercept here gives actually 1 over Vm. So if you look at the given question, so this data is given as 0.0026 centimeter cube inverse. All right. So therefore, from this, we are supposed to find out the Vm, the volume required to cover the complete monolayer. All right. So let's clean the board and work it out, the rest of the numerical problem. Okay. So a correction over here. So this is actually 0.0065 centimeter cube inverse. So that was given. So therefore, this intercept is Vm inverse is 0.0065 centimeter to the power minus 3. So now I want to find out the volume V. So V should be inverse of I, and it would give rise to something 0.154 centimeter cube something, okay. And so here now what happens, that this volume is given at STP, standard temperature and pressure. So immediately we can convert this thing into liter. So hold on, so this actually comes to not 0.1, so 154 centimeter cube. So okay, pardon for my mistake. So this comes to 154, I have rounded it up here, 154 centimeter cube, and so therefore if we convert it into liter, it becomes 0.154 liter. Okay, and we all know that at STP 1 mole of gas would occupy 22.4 liter. So therefore number of moles would be equal to 0.154 divided by 22.4. Okay, and so the number of molecules should be equal to 0.154 divided by 22.4 multiplied by the Avogadro's number, and each molecule has a cross section that is 0.43 nanometer square. So we have to multiply that many number of molecules with the cross section so that we get the total surface area. So the total surface area is equal to 0.154 divided by 22.4 multiplied by 6.023 into 10 to the power 23 multiplied by now 0.43 nanometer square. So the question is what value we should write for the nanometer square. So 1 nanometer is equal to 10 to the power minus 9 meters. So nanometer square means it should be multiplied with 10 raised to the power negative 18 meter square. All right, so you see up to this much all are numbers, so the unit comes here as the meter square. So we have to solve it. So if we solve it, so the final value would come somewhere near about 178 meter square. Okay, so you can try that out, whether you come to this value. All right, so this is the approach to solve this problem. In fact, this is the practical method by which, using Langmuir's equation, one can assess the surface area of a solid. And the data that was given, it was taken from a practical experiment. So these are some real life data. And this is how it also explains that why this adsorption process is so important to us, because we can not only follow a heterogeneous catalytic mechanism, but at the same time we can get the surface area of a solid. All right, so this much was the tutorial problems given to you for solution, and next I would discuss the 10 assignment question, or the 10 questions that I set for you for the class quiz. So I'm going to delete this board, and I'm going to explain all those quiz questions one by one. All right, stay put. So we start with the question number 1 from the class quiz. So it was set as a multiple choice questions. So the first question gave you a mechanism for the formation of CaCl2. So this is the mechanism, 4 steps, all are irreversible steps, means unidirectional. And the question asks you to find out the rate of formation of CaCl2. So therefore, we already know that if nothing is mentioned, we can apply the concept of steady state approximation. So dCaCl2 dt from these steps straight away gives this expression. And then we have the intermediate COCl. So we can apply the dCOCl dt is equal to this. So we get it from here. And applying steady state approximation, we can set it to be 0. So immediately we get this expression from here, that this is equal to this. So we can replace this is equal to K2ClCO. All right, and then whenever we express it like this, again we get a new intermediate Cl. CO is a starting material, so therefore it is fine. So now we have to find out expression for Cl. So now once again we are going to apply the same steady state approximation for Cl. So the expression goes something like this. So please be careful not to miss these two factors too, both first step and in the last step. So if you look at this, there is a term appearing here. So if I take the bracket, so this becomes minus. So obviously we have seen that this part is equal to 0. So this becomes 0. So therefore, whatever we find that 2k1cl2 is equal to 2k4cl square. So from this we can find the expression for Cl is this. So therefore we can find the rate of formation of CaCl2, that means dCaCl2 dt is equal to K2 multiplied by Cl. So the concentration of Cl, we can write K1 divided by K4 whole to the power half multiplied by Cl2 to the power half multiplied by CO. So this is the final expression for dCaCl2 dt. So if the given the numerical data, you can fill it up the values of K1, K4, K2 and all the Cl2 CO, and you can end up with the answer. So alright, so let's move on to the question number 2. So the question number 2 tells the same problem that we have solved a while ago, that a gas G2 gets dissociatively adsorbed into two G atoms. K is the equilibrium constant and Pg is the partial pressure of the gas G2 which is measured. So what would be the expression for theta? So obviously now we know that theta would be root over of K Pg divided by 1 plus root over of K Pg. Alright, so you can refer to the solutions that I have just done in solving tutorial number 4 if you still get confused that how we arrive at this expression. All right, so let's move on to question number 3. So question number 3 says that in a certain inhibition mechanism with increasing I, or the concentration of inhibitor, the apparent Km increases but the maximal velocity remains constant. So what is this type of inhibition? So the answer is, it is competitive inhibition. And the hints of the answer is our earlier lecture on enzyme inhibition. You can refer to that lecture video, and also the tutorial number 3. Now the next question was that in a non-competitive inhibition with increasing inhibitor concentration, what happens to the apparent Km? And the answer is, it remains constant, unchanged. So once again, the answer source are the same, the lecture on enzyme inhibition and also the tutorial number 3. So we move on to our next question, that is question number 5. So question number 5 gives you a mechanism. It's a 3-step consecutive reaction. So the first step, rate constant is K1, in the second step is K2, and the third step it is K3. And also the activation energies at each corresponding steps are given. So if for the first step EA1, second EA2, and for the third it is EA3. And the question also says that Mg is a catalyst. Okay, and it asks you to find the activation energy of the overall reaction when X3 is extremely high. So therefore we have to find out the rate law for this entire overall reaction. So if we apply the concept of steady state and do all our calculations correct, so we would end up with an expression something like that, 2k1 k3 multiplied by x3 whole square divided by k2 x3 m multiplied by concentration of m plus k3 x3. All right, so this expression you can all right, also, so there is a concentration term m would appear here. So if you do all these things correctly, then this should be the final expression, and then you apply that when x3 is extremely high. When x3 is extremely high, so we can neglect this term with respect to k3 x3. So therefore this red expression would then be reduced into something like 2 k1, and we have x3 multiplied by m. So now you see the rate constant here for the overall rate is k1. All right, or twice of k1, whatever. So we would concentrate on k1. All right. So therefore, if we talk about the activation energy, so the activation energy according to the Arrhenius equation would depend on k1. All right. So k1 is related with the first step where activation energy is E1. So given the choices, the correct answer would be EA1. So the activation energy corresponding to the first step would be the correct answer, since the overall rate is governed by the rate constant of the first step, which is this one. All right, so now we move on to the question number 6. So question number 6 says that for the following reaction, the rate constant is something like this. The value is given and it asks you to find out the order. So by looking at the dimension of the rate constant, you see this is concentration inverse, second inverse. So that means the order is 2. So it's a second order reaction. And next we go to question number 7. So this is pretty much the similar problem that we just have solved initially in the tutorial number 3. Tutorial number 4, that means the tutorial on heterogeneous catalysis. So here 1 over V versus 1 over P curve is given, and it's obviously an adsorption of a gas on a solid surface, and it asks you to predict the number of molecules required to have a monolayer coverage. So that means it asks you to find the NM. So therefore we go by the same logic. So from this graph plot, if we extrapolate, so therefore we come at here. So this is the intercept, and the intercept says that this value is 0.0026 centimeter cube inverse. So therefore our VM should be the inverse of the intercept I. So this becomes something like 384. So 1 over 0.0026 centimeter cube. It becomes 384.6 centimeter cube, something like that. And so since we know the Vm, so therefore we can try to calculate the number of moles. So the number of moles is equal to 0.384 liter divided by 22.4, and therefore the number of molecules required to have a monolayer coverage, that means it is essentially Nm, is equal to 0.384 divided by 22.4 multiplied by the Avogadro's number, and this number would come to something like 10 to the power 22. Okay, so that would be the answer for question number 7. All right, so let's move on to question number 8. So question number 8 says that in mixed inhibition, apparent Vmax is given by Vmax by divided by alpha prime. So what's the expression for alpha prime? So we have done this expression for alpha prime during our lectures, as well as our tutorial number 3 on homogeneous catalysis. So the alpha prime involves the reaction of enzyme substrate complex when it gets attached to the inhibitor and forms enzyme substrate inhibitor complex, and correspondingly the expression for alpha prime is 1 plus inhibitor concentration multiplied by equilibrium constant, and this is a constant value, equilibrium constant, and I is a variable. An expression for the equilibrium constant is given by this. So therefore the correct expression for alpha prime is given by this equation. All right, so this is the correct answer. So now let's move on to the question number 9. So the question number 9 talks about a parallel reaction, X going to Y and Z with the rate constant K1 and K2 respectively. It's given that the value of K1 is 0.001 second inverse, and the ratio of the concentration of the product Y is to Z at any time t, or at a certain time t, is given as 0.25. What is the value of K2? So therefore we can say that the Y divided by Z, concentration ratios of Y is to Z at any time t, or at a certain time t, is equal to the rate of formation of Y versus divided by the rate of formation of Z, and that is equal to K1 concentration of X divided by K2 concentration of X, or basically K1 divided by K2. And now this value, that is K1 divided by K2, is basically the ratio of concentration of Y is to Z at any time t, and that is equal to 0.25. So therefore we have to find the value of K2. So K2 is 0.001 divided by 0.25 second inverse. So that is equal to 0.004 second inverse. That's the answer. So next we move on to the question number 10. So in question 10 we have a very straightforward situation. So in a consecutive reaction, A going to B and B going to C, with the rate constants K1 and K2 respectively. So if the species B has a transient existence, then what would be the most appropriate relation between K1 and K2? So that means B has a transient existence. So that means B during the reaction is formed by a very small amount, and that amount stays almost constant throughout the reaction. So it appears like the B has not formed at all, and if it is formed, it does not have an influence in the reaction. So this is only possible where the first step, that means the first rate constant, is negligibly small with respect to the second rate constant. So that is the answer choice among the 4 given options. All right, so these are the 10 questions solved from the class quiz I have taken. So and that's all about the course lectures as well as the tutorials. So I hope you enjoyed these video lectures. So now it's your job to study the materials from the textbook and from the video lectures, and get prepared for the upcoming tests or the end semester examination. So I wish you all the best and good luck. Thank you.